here is the matrix solution phi to the equation phi prime equals A phi, where A is this matrix. Now this system is the same as this system. We haven't used the methods that we've used so far in solving this system. We've chosen to diagonalize the A matrix using our similarity transform, and then to inverse transform that diagonalized matrix. And here it is, and this should be a solution to our system. In what sense? Well, just as our T matrix has our two eigenvectors, just by analogy if you wish, the columns of this matrix form our solutions to the system. So this is a two-column matrix. I write it as phi equals y1 comma y2, vector y1, vector y2. Now here's where notation gets confusing, and as I've said, and probably said on video before, I haven't arrived at a good way to make the notation any clearer than what I'm doing. And this is pretty much equivalent to the notation your book uses, but hopefully it clarifies things a little. Okay. So y1 is this column, y2 is this, y1 vector is this column, y2 vector is this column. Don't confuse y1 vector, y2 vector with the y1 and y2 in the system of equations. These are vectors. These are simple scalar functions. These are vector functions. They have two components in this case. Okay. Another comment, phi is just another psi matrix. We've been doing psi matrices. We've been solving systems and putting the solutions into columns and checking the Wronskian to make sure everything is linearly independent. And we've been doing that for quite a while. We're used to doing that. That's our psi matrix. And we even use the psi matrix to get a propagator matrix and so forth. So phi is just another psi matrix, but we call it phi because when we start here, we don't have any solutions. We don't have a psi matrix. So phi is just the psi matrix that's going to be the psi matrix for the solution we get here, but we call it phi when we write out the equation. And now it's just another psi matrix. It's a psi matrix that we could get by solving this system by ordinary methods. But we've bypassed those methods and used vector methods, diagonalization and exponential of a matrix. And we've obtained this without that headache. And this is actually very efficient. Okay. You'll love it once you get used to it. We want to remind ourselves what y1 and y2 are. So you want to do this. Okay, once you get down to this matrix, you say, okay, here's our phi matrix, that's our y1, y2 vectors, okay? And our fundamental set is the set consisting of y1 and y2, and that equals, well, y1 is this column, well, I'd write out this column here, and y2 is this column, I'd write that out here, and I do that elsewhere, didn't have room to do it here, but you want to write it out. You want to write out exactly what I've written out and fill in these columns here. And of course, then you see that your y1 is this column and your y2 is this column. This is the first column, this is the second column. Real important to understand that. Now, a notational thing that I inserted here to make it hopefully as clear as possible is that your y1 vector consists of a y1 and a y2 function. Okay? And your y2 vector consists of a y1 and a y2 function. Now, the y1 and y2 function you get here, well, here's your y1 and y2 function for your y2 vector. Here's your y1 and y2 function for your y1 vector. Now, I can't call this y1 and call this y2, and at the same time call this y1 and call this y2. But that's what they are. They're a y1 and a y2 that satisfy this system. So what I call them is, instead of, here's, this says y1, this says y2, but this says y1, 1, and y2, 2, meaning the y1 and y2 vectors for my y1 vector solution. So this is the y1 for the y1 vector, so we call it y11. Here's our y11 function, our our 2,1 function. And similarly down here, we got a y1 and a y2 function, but they're for the y2 vector, so we call it y12, y22. Of course then, the y11 is this, which is in the 1,1 position of this matrix. The y21 is this, which is in the 2,1 position of this matrix. And the y12 is this, which is here in the 1,2 position in this matrix. And y22 is this, which is in the 2,2 position. So it all corresponds to our typical IJ notation for a matrix. And it goes without saying, this is all extendable to any number of equations and any number of variables, okay? Okay, a system of n equations for n functions. So there's some notation. We really have to be clear on this notation, otherwise we completely lose our way, we forget what we're doing and why we're doing it and what it means. Well, the next thing to do is see if this vector and this vector are both solutions to this system, because if they aren't, then everything we've done is in vain. Okay? We've done all this stuff that has nothing to do with what we're used to doing to solve a system, even though it is related at a deeper level. And I claim that we've got a solution to the system. Now, at this stage, you know, naturally I'm a little nervous. I'm hoping I did it right, and I don't always do it right, as you know. You know, I can write down things wrong, I can miss a sign, I can miss a coefficient. And it looks like I wrote something down wrong there temporarily, but I think I corrected that right away. Okay, anyhow, is this a solution? Is this a solution? That's our next question.